My name is Audrey, and I'm a first-year student in the RISE Lab, co-advised by Professors Jan Stoika and Natasha Crooks. Today, I'll be presenting on our work on RAMP-TAO, which is done in collaboration with Facebook. So a quick overview of the project. The goal was to provide stronger transactional guarantees for a system that serves over 10 billion reads per second. And this is important because we want to prevent anomalies that could impact end users. And we do so by presenting a novel protocol that we call RAMP-TAO, which is able to serve over 99.9% of read transactions from the local cache instance. So first, I'll give a quick overview of TAO, which is Facebook's online data store for its social graph that stores nodes and edges. So the system serves a very challenging workload. And because of this, the original designers decided to prioritize performance, availability, as well as massive scalability, and decided to make it eventually consistent, meaning it doesn't have any isolation or consistency guarantees. TAO's original goal was to be able to do a few things well at scale, so it had a very simple API that had no transactional semantics. And in terms of its architecture, TAO essentially consists of two graph-aware cache layers that sit on top of MySQL instances, and updates are propagated via asynchronous replication. So the first question we ask is, why do we need transactions, and why do we need them now? In recent years, there's been a shift product developers from accessing the system directly to using a higher level query framework called ENT. And ENT makes it easier to express complex operations over the social graph, and also provides a natural transactional boundary. So adding these semantics would greatly reduce developer burden. And I'll give an example next for how transactions can be useful. So let's say we have a user, Alice, in our social media product, and she's a musician. She wants to share both the sheet music as well as the recording of a new piece that she's made. And if she was able to make all these updates within a transaction, she can ensure that these updates are observed together. We want to prevent the case in which we're able to see her sheet music, but not her new recording, and vice versa. And this phenomenon is called a fractured read, meaning only a part of a transaction's updates are captured. So we actually need two types of guarantees to do this. We need failure atomicity on the write side and atomic visibility on the read side. So failure atomicity is the property that all parts of a transaction are either aborted or committed. And this is guaranteed by TAO's write transaction APIs, which were added in recent years. We also need atomic visibility, which is the guarantee that all or none of any transaction updates are visible to other transactions. So this would prevent the case we previously mentioned. And this is not a guarantee yet provided by TAO. TAO doesn't support any read transactions currently, only write transactions. So the first part of this work asks what happens without this guarantee. We complete a measurement study in which we first model projection data, since we don't have read transactions yet, but we do have very complex queries that involve multiple accesses to TAO and should be served in a read transaction. And we generate the workloads with this projection data, and we check for anomalies within these generated read transactions. We find that there are over 6,000 anomalies in the 10 million read transactions we test, meaning that 1 in every 1,500 batch reads that are currently occurring could violate atomic visibility. And we find that these read anomalies actually eventually resolved after the corresponding write transactions they overlap with are fixed through a two-phase commit recovery process, but this can take up to 30 seconds. And remember that we are serving 10 billion reads per second, so there's quite a large window in which these anomalies can occur. So through a measurement study, we find these anomalies do occur though frequently, but their rarity is actually a source of complexity because they are non-deterministic and they're hard for developers to debug. So the measurement study really motivates a need for retransaction API that guarantees atomic visibility. So now we ask, how can we ensure this property at the massive scale that TAO operates at? As our starting point, we look at the read atomic multi-partition or RAMP protocols, and these are the first protocols that explicitly ensured atomic visibility. But we find that we can't directly apply them to TAO. And this is because there are three main challenges we need to address. The first is that most read transactions must be fast for TAO, meaning that they should only take one round to the local TAO instance and shouldn't require too much additional processing, while the RAMP protocols always require additional checking for each transaction it serves. Also, the metadata that the original protocols need is excessive in terms of overhead, and to gather this metadata currently, we would need multiple round trips to the database within TAO. Finally, the original protocols require multi-versioning support to guarantee redetermination, but both TAO and the database lack multi-versioning. To address these problems, we present the RAMP-TAO protocol, and we make the key insight that we only need to ensure atomic visibility for recently updated data. We leverage this to minimize the performance and memory overheads that our protocol incurs. So we make changes to the refill library, which is a recent writes buffer in TAO that stores the past 3 minutes of global writes for our protocol. The first, addressing the first challenge we mentioned, is we add a bit to indicate if a data item has been modified by a transaction recently. And this allows us to check locally if the result we have is already atomically visible by default, if none of the keys involved were part of the same write transaction, and we can return to the client immediately. We also use a low watermark timestamp to distinguish between updates we haven't seen yet and updates that are already evicted and safe to return to the client. We also add transactional metadata to the refill library. This includes caching the versions and full transactional write sets, and this information makes it very easy to check for atomic visibility. We also support limited multi-versioning within the refill library by modifying it to store additional versions, and garbage collection happens naturally through first in, first out eviction, which is already implemented, so we don't need to make any additional changes. So the fields we add to the refill library, and we also support multiple versions. So with this protocol, we evaluate it and find that it can be feasibly deployed in production. It's currently implemented as a standalone service that's used to monitor the anomalies of current write transactions. And we find that over 99% of these read transactions are able to complete within one round. Furthermore, our tail latency is comparable with that of TAO's, indicating that the performance overhead is acceptable. And we note that the data shown here is including accesses to the database, which will no longer be necessary once we make the changes to the refill library. In terms of memory overhead, we find that 14% of updates currently involve multiple versions within the refill library's retention window, and 3% of these are transactional, meaning that our protocol incurs a 0.42% decrease in the buffer size, which is minimal, and we have limited impact because we're only storing transactional information for the recent past. An important lesson we take away from this work is that we should only provide stronger guarantees when necessary, and we should only impact users that require these guarantees and make sure that we don't incur any additional overhead for which the eventual consistency of TAO is already sufficient. Our layered approach to stronger isolation is similar in spirit to the bolt-on strategy, in that we decouple the concerns of availability and replication from consistency and isolation guarantees. So we find that an architectural separation is very effective for large-scale systems. The database is responsible for durability and replication, while the TAO caches make sure there's high availability as well as low latency. And RAMP-TAO here ensures stronger transactional guarantees, and the application logic, essentially the AMP framework, runs on top of RAMP-TAO. In summary, we've covered a protocol that can guarantee atomic visibility for a system that runs at massive scale, and our protocol is able to serve the vast majority of read transactions within one round and with minimal metadata. And we find that our layered approach to strong guarantees works well and can be applied to other large-scale systems. Thank you.